So hello everyone and welcome to this next lecture on Python Power Electronics, and in this lecture I'm going to talk about how we use the circuit simulator in the command line interface and also how you generate plots. I have created another file for plottings and I'll show you that in this lecture also. So to begin with, I'm going to start in my usual virtual environment, and I'll just do pwd. So this is where I left off in the previous lecture. Now the previous lecture I created this virtual environment, that is in this particular one, and I created a sample file here. Now this sample file, which is sample simulation, which is a diode rectifier, was run with the web application, that is PPE web app version 2.0.5. Now what I'm going to do in this case is I'm going to run exactly the same simulation with the command line interface. Okay, so I'm going to tell you how nothing changes. It's exactly the same simulation, it's just that the application is different. And one of the reasons why I would like to say this is that even though the web simulator is available in two different flavors, that is the web application and the command line interface, both of them will be maintained equally. That is, I use both the web application and the command line interface. Matter of fact, my preference is for the command line interface because it's much faster that way. So the web application is mainly for those people who would rather prefer some kind of a better user interface than a command line interface. Though I cannot build a GUI, a web application was as close as possible. So to begin with, I'm going to go to the web browser and I'm of course going to go to my website. So for that I'm just going to Google Python Power Electronics and I shall go to my site. So first I go to downloads because I'm going to go and download the latest version. Now as of the time of making this video, I am gradually beginning the migration to Python version 3, and that's this version. So on May 1st 2018 I released the first version, which is compatible with Python 3. I'm not going to use it in this lecture because this is still in testing mode. I would like to continue developing the simulator with both Python 2 and Python 3 for maybe 6 months or a year, because Python 2 is going to be available till 2020, after which it will be deprecated. So let's go over to the latest version of the command line with Python 2, and that's this one. So this is explicitly mentioned command line by interface with Python 3. If it's not mentioned, it is with Python 2. So let's go and download the zip file, and I shall go to my virtual environment. No, not diode rectifier. So I'll just save it here. So I shall save it in that file. And at the same time, I have released a new file, which is a MatPlotLib plotting file. Okay, this is just a plot file that uses MatPlotLib, and if you're using the command line interface, you can either use GNU plot or you can use MatPlotLib. So I'm just going to download this also. So let's go back to my web browser, or rather my file browser. So now I have these two files which I just downloaded. This was the web application, which is before. This is a dummy test file. So I'm going to extract this, and let me also extract the plot file. So I now have two files. The command line interface has these files, and it also has an install.doc file, and it has a license.txt file. But the others are the simulation files. Okay, let's go back to this one. PPE plot has only one file, which is the plot file.py file. This is the Python file, and this is just a readme file with some instructions. And you can open this and check it out. So that's it. This just tells you what you need to do. You need to install MatPlotLib if you want to use this. If you don't have MatPlotLib already, that is. So I will go through this in this lecture. So now that we have this, let me go back to this file. Now in this file we have four major files. That is, we have source, or rather three. We have source, direct.csv, direct.csv, load.csv. These are the three circuit files that we create. The rest of the files are not ours. These are some dummy files that I created just to show you the errors which could be produced. Test file is a file that the simulator creates, and these are the data files. So we are not going to get into that. What we're going to get into is only these three files. I need these three files. So what I'm going to do, I'm going to create another folder. So I'll call this diode, let's call this CLI. And I'm going to copy these three files into this new directory. So that's it. So I'm starting off with just three files. Now what I'm going to do, I'm going to go over to my pp.cli. So this is the command line interface. This is the one which, this is the file which I just downloaded. This is the simulator in the command line interface. I'm going to copy all these files and I shall put it into this new folder, that is diode.cli. And this is something you need to do. If you're using the command line interface, you must have all the simulator files, that is, you must have those 6 files. You can even copy these install and license.txt, that doesn't matter, but you must have all the simulation files from this simulation directory into your working directory. Okay, and then on top of that you must have your simulation files. This is how it is. So now that this is done, I'm going to go over to my command line interface and get started. So to begin with, let's do a D. So this is my diode.cli. First and foremost, I need to activate my virtual environment. So let's do that. That is source python2 test bin activate. This is the command needed to activate it. Now you see python2 test comes up here, which means I am now in my virtual environment. Just do a little test and I have Python 2.7.13. No problem. This is exactly what I want. Now that I have this, let me go into my new file, diode.cli. This is the new directory which I created. This has all the circuit files, that is the simulator files that I just copied, and it has the three circuit files which I copied from the previous simulation. So let's get started. So now the way to start this simulation is you got to say Python circuit solver. Circuit solver is the main file which launches the circuit simulation. All right. In Django you would do python manage.py run server. Here you do python circuit solver.py. That's all you do. This is basically like saying run or pressing the run button in a simulator. So now in the command line interface you must read these instructions. So this is what it says. This appears to be a new project, and it is because we just created the folder. A sample circuit inputs.file has been created. This is the second file, the second line. Circuit inputs.csv file has been created. Enter simulation parameters in the file circuit inputs.csv file. So enter simulation parameters. So let's go check out what this file is. So we are in this folder. I'm going to look for circuit inputs. This is circuit inputs.csv, and I'm going to open it. It is a spreadsheet. It is a CSV file, that is a comma separated value file. So it can be opened with any spreadsheet software. So I'm going to open it with my spreadsheet software in Linux. If you're on Windows, you can use Microsoft Office. So this is the file. Now if you compare it with the previous lecture on using Django, that is how you simulate it with the web application, everything was done using forms. Here I use spreadsheets. All inputs from the user are from spreadsheets. So if you see here, these are all the parameters of the simulation which were there in the first page. Here it is there in different rows of this circuit file. So let's read each one. So the first one, name of the circuit file. Change the name of the file to the circuit file. The file has to be a .csv file, so do not use another extension. So here I got to put all the circuit files that I'm using. So let's go back here and look at my circuit files. What do I have? I have three files: source.csv, load.csv, direct.csv. So I'm going to put these two, both these three. Now the way to do it is you have to put them on different cells in the same row. Okay, you can't put it in the same cell. Don't put it with a comma. Don't separate it with a comma. So source.csv, direct.csv, and do not forget the .csv. It'll throw an error without that. And finally load.csv. So these are the three files which I'm going to use. Then let's go to the next line. Time duration of simulation. This is the time in seconds, similar to the previous case. Let's do just 0.5 seconds. That's enough. Third line. Time step of the simulation recommended to be less than 10 microseconds for accuracy. So it's by default 1 microsecond. I think that's good enough for this. You can change this to 10, 5, or you can even decrease it to like 1 nanosecond, anything you want. Time step of data storage. As before, this is the frequency at which we store data. This has to be greater than or equal to the time step of that is the integration time step. Name of the data storage file. This is very important for us. Okay, in the previous case it was not so important because we would plot everything in the web application, but now we are going to plot it on our own. So it is very important that you choose this file. For now, this is good enough. Circuit output.dat file. The last, name of control files. Now there are 3 files. Add or remove as many control files as needed in separate columns. Now at this point of time I have not talked about control, so I don't want to talk about control here either. So what I'm going to do is I'm going to delete all these files. I don't have any control. Though I have one control element, that control element does nothing. The switch is completely open, so it doesn't work. Next one, 7. Split the output file. Say yes if you think the data file is too large and plotting is taking too much time. Okay, let me just zoom in case you need. Okay. So if you say yes if you think the data file is too large and plotting is taking too much time, or else say no. Now here again, in the previous case I said you could say yes or no. I'm just going to say no. If you want to say yes, you can say yes, and then you can say length of the time windows. So you could just say, like for example, if this is 0.5 seconds, you can say each one can be 0.2 seconds, 0.2, 0.25, whatever you want. So if you say 0.2 seconds, it'll break it up into 3 parts: 0.2, 0.2 to 0.0 to 0.2, 0.2 to 0.4, and 0.4 to 0.5. So, but we don't want to do this, so I'm just going to say no. Sorry, I'm going to say no here, and I'm going to delete. And I'm going to delete this. So this is my circuit inputs.csv file, or these are the simulation parameters. So that is put in circuit inputs.csv file. So remember, if it's a starting simulation, the simulator will create an empty, a sample circuit inputs.csv file, and you change it. If it has already been changed, it will not change again. It will remain its previous value. As before, it just gives me a warning. Do you really want to save it as .csv? I say yes. Now let's go back to this. So we have done this. When done, close the file and press yes, and enter to continue. So let's do that. It says close the file, so we shall close this file and say yes to continue. So now it tells you some information. This was not there before. Here in the command line it tells you, it says the number of nodes is equal to 12, the number of branches is equal to 18, the number of loops is equal to 7. And then it says the following circuit schematics have the corresponding parameter files. You see, source.csv, source params.csv. We never created this file. We only copied this source, direct, and load files. We did not create or copy these files. The simulator has created them. What are these files? These are parameter spreadsheets. Each circuit file will have a parameter spreadsheet. So you see what's happening? Source.csv has a parameter spreadsheet called source_params. It just adds this underscore params. Alright, so each of them has one. Enter the parameters in the files above. When done, close the files and press yes and enter to continue. So let's go back and do that. So I'll go back to my folder. Let's start with source. So this is source.csv and this is source params.csv. I'm going to open it with my Excel sheet. So let me open it. So here in the previous case, we saw that it was all in the case of a form. We could click on a button, it would edit, it would create an edit form. Here everything is a spreadsheet, and these are different rows in a spreadsheet. Similar concept. Now if you see in the web application, when we went into the form, every element has default parameters. The same thing here. Every element has default parameters. You can leave it at the default value or you can change it. So for example, inductor. The inductor, let me open the circuit file also so that we know what we're doing. So the inductor is inductor V single phase source 1. Let's go back to our parameter spreadsheet, and that is this one, inductor V single phase source 1. It is saying 1 millihenry. Now as we did before, 1 millihenry is too large, so let's reduce it to 100 microhenry. That's good enough. Now let's go back to ammeter source 1, or rather let's check out what it is. Ammeter source 1 is at position 1A and its positive polarity is pointing towards 1B. So let's go back and look here. So this is ammeter source 1 at 1A and the positive polarity is 1B, which is exactly what we want. So let it be as it is. Resistor. The resistor is V single phase source 1 at 1F and is 100 ohms. So let's see what this is. So resistor V single phase source 1 at 1F. So this is a parasitic resistance of the source. It does not have to be 100 ohms. This has to be negligible. So let's change it. This is 0.01, 10 milliohms. That's good enough. The next, voltmeter source 1 at 4J. And therefore this is the voltmeter, this is the voltage, voltmeter at 4J. So this is the voltmeter at 4J. This has to be a positive polarity towards 3J. Let's look into it. And this is positive polarity towards 5J. You see, this is a mistake. It has to be towards 3J because the positive polarity is upwards. Next, the rated voltage that should be measured. As I said before, it's always best to have this rated voltage level to be much higher than the voltage that is expected. Right? So let's make it 1000. So now the last one, voltage source at 1D. That is, this is the voltage source. This is of course the most important component in this circuit. So let's eliminate. So peak volts 120 volts. Now as I said before, we are going to simulate a 120 volt system, 120 volts RMS, which means it's probably 170 volts. I'm going to change this to 170. The frequency is 60 Hertz. In North America at 60 Hertz, in Canada that's where I am at 60 Hertz. If you are in Europe or India or anywhere else, change it to 50 Hertz. The phase 0 degrees, it doesn't matter because it's a single phase source. If it's a 3-phase source, you would have to change this. You would have 3 different sources and all of them would have different phase angles to make sure that they are phase shifted from each other. Here it doesn't matter. DC offset, it's an AC source. You don't need a DC offset, so it has to be 0. Positive polarity towards 1E. Now, the element is at 1D. Positive polarity towards 1E. What that means is, in my circuit, this is my element and the positive polarity is towards the right, and that's exactly what I want. So this can remain as it is. So we have edited one sheet. I'm going to save it and I'm going to close this. So let's also close this one. Now let's go to the next one, which is the next one, direct.csv. So let's check that out. direct.csv. Let's open it. So this is the circuit file. Let me now open the parameter file. The parameter file is direct_parameters.csv. Let me go back and change and open this. Okay, so you see these are only the diodes. There's almost nothing else here. Very convenient. So you see how convenient it is when you break up your circuit into blocks. You have very easily reusable components. So here what I got to do is check diode direct 1 D4 at position 16i. Okay, now first things first, let's change the voltage level of all the diodes. As I said, we want, just like the voltmeter, the voltage level of the diode has to be much higher than the actual existing voltage level of the circuit. So let's go to 1000 volts, and here I can just copy this cell. This is a very convenient feature in, so you see, I just, this is necessary. So you could just, I don't know why there's so many zeros actually. So, but anyway, so I am making the voltage level of all the diodes to be 1000 volts. So let's now go and check out the polarities. So direct D1 is at 16I. Let's check out direct D1. 16I, row 16I is this one. Now in a diode rectifier, such a diode bridge rectifier, all the diodes have a cathode pointing upwards. Okay, so the cathode is towards the upward direction for every diode, which means if for 16I, the cathode should be upwards, either 15, 14 or 13. So let's change that, because it is at 17I. So we shall make it 15I, 16, this position is a 16I, the cathode is towards 15I. 16E, again the same, 15E. Then the diode is at 4I, we shall change it to 3I. Just to give you an idea, let's go back here. You see, this is the diode at 4I, diode direct 1 D3 at position 4I. As I said before, cathode is upwards, which means cathode position should be, cell position should be 3I. And the last, same for the D1, that is at 4E, it goes to 3E. So these are the simple parameters of the diode rectifier. We can close this and we can close this. So the last one has come up here. The last one is load and load parameters. So let's open those two files. So this is the circuit and this is the parameter file. So I have several. Let me go through each of them. First step first, resistor load 2 at position 10I. So let's see what it is, and that's 100 ohms. So resistor load 2 at 10I. Now this is a resistor which is in series with the switch. Alright. At present the switch is open. Like I said, we don't have to have any control in this simulation. There's no control. So this switch does not work. So doesn't really matter what this resistor is. I can change it or I can leave it. I'm saying let's leave it, because if it's not going to matter, why do you want to change it anyway? So this stays as it is. So let it be at 100 ohm, it doesn't matter. Capacitor, DC bus, 8C. This is very important. Let's go check it out. This is capacitor at DC bus at 8C. Now this capacitor forms the DC bus of the load. The diode rectifier produces a fluctuating output. The capacitor smoothens that voltage. So this is a very important element. And first one is the value of the parameter. The value of the parameter now is 10 microhenry. Like I said, we need this much bigger. So let's increase this to 1000 microhenry. The next one, positive polarity towards cell 9C. Now this is the capacitor, and this is the positive term upwards. So which means that the positive polarity should be upwards and not downwards. So let's go change that. Let's go change this to, sorry, this is not 8C, this will be an error. It cannot be the same position as the component. So now I'm moving it upwards, that is one cell upwards to the component. Voltmeter 10E. Let's check it out. This is the voltmeter, it is at 10E. The positive to polarity should be upwards. So let's check it out. The positive polarity is again down. So we're going to change this to 9. Just a little note here, the polarity of elements is always random. You can never take it for granted, so always go and check. And of course the rating voltage level, we shall increase this to 1000 volts. Switch. Now this switch, as I said before, we don't really care about. So there is a switch, load 2, it is at 5I. just for the sake of safety, let's increase the voltage level to 1000 volts. Even though it is off, let's make sure that it draws a negligible current. Now the rest we are not going to even worry about now. The default is control, that is the name of the control signal. Now I would say this, if you want you can change it, but since we don't even care now, we can leave it as it is, doesn't matter. Ammeter load 1 5G, let's check it out at 5G, so at 5 and G, so that's this one. The ammeter load 1, the current goes downwards because the positive terminal, the upper terminal is the positive terminal, lower terminal is the negative terminal, so current is going to flow downwards, which means the positive polarity has to be towards 6G or above, or more, and let's check it out. Oh, 6, yeah, so positive polarity is 6G, so it can be as it is. Resistor load 1 at 10G, let's check it out. So row 10, cell G, that is this one. So this is the main resistor in the simulation because there's only one load resistor, the other one is inactive because switch is off. So let's decrease this to, let's say 10, or let's say more, let's make it 15. The resistor DC bus at 13C, let's go check it out. So this is the resistor at 13C. This is a parasitic resistance to the capacitor. As I said in the previous lecture, in the lecture for how you simulate with a web app, every branch must have some resistance, finite resistance. If there is only a capacitor in the branch, this is a pure capacitive branch, which in the simulator is illegal. You must add a minor resistance to it, resistor DC bus. So this is a parasitic resistance. It has to be negligible. And it is now 100 ohms. 100 ohms is not a parasitic capacitor, so let's decrease this to 10 milliohm. That's good enough. So let's save this. I think everything is done. Let's close the file and let's close the circuit file. So let's come back to our command line. So we have entered the parameters and on the files. We have closed the files. Now we are ready to go. So let's press enter, Y and enter. And the simulation is running. So you see, now in this case, this tells you, now a lot of other things also happen. For example, here, this is an output. This output is totally unnecessary. I had it initially just for debugging purposes and I never got rid of it. This just tells you all the components that are there in the entire simulation. So this is all 3 spreadsheets together. Alright, so in a really large simulation this will be a huge list. You don't really have to worry about it. If you want, you can actually this is just in case you want to cut, copy, paste it into a .doc file just to sort of list out all the components you have. It's up to you. The main thing is here. You see, this shows you the output file. Now, the output file is our circuit output.dat file, and this tells you how the variables are written to that output file. You see, we have 4 meters. All these 4 meters are plotted in that circuit output file along with the time instant of the simulation. Alright, so this is how the plot happens. Now at this point of time, simulation is running, let it run. I am now going to go and check out. I'm going to go and check out the plot file. So the plot file is a Python file. So I'm going to open this Python file. Let's open it with a text editor. That's all I need. So this plotting file uses several of these. It uses math, it uses MatPlotLib. Don't worry. There are 2 things which you need to do. First things first, always check in this line. This opens the circuit output file. Okay, it opens the output, that is the output data file. In our case, the output data file is circuit output.dat file. So this can be as it is. If you have changed the name of the output data file in the circuit inputs.csv to something else, let's say you changed it to plot1.txt, alright, that's perfectly okay. In that case, come here and change that value, plot1.txt, the entire file, including the extension. Don't have to change anything else, just the name. So now that this is done, you can come all the way down. So you see what here, there are some I put in some instructions. There are basically two of them. Basically I have put in two different type of variables. So the first thing is each plot should have these two files. Okay, should have these two lines rather. The first is the actual plot file that plots the time along with the index of the variable. So now, just to know what this is, let's go up here. I am reading my data file and I'm splitting them up into different arrays. So now time is in one separate array, time points. However, the others are in these variables. Now this again is a multi-dimensional file. So y1 is an array, y1 is a list, y2 will be a list, y0 will be a list. So now the question is, how would you actually plot your file? So let's go up here. You need to map these plots with this file. So let's say, for example, let's say I want to plot voltmeter source 1. If I want to plot voltmeter source 1, then I need to come to this txt file and I need to change this to 3. The reason why 3 is because Python array indexing starts at 0, whereas this is not starting at 0. Alright, this is starting at 2. So it is, if you want to count this file, you would count it at, if you see this counts at 1. So how would this be in the index file? Y of index 0 is time, y of index 1 is this ammeter source 1, y of index 2 is ammeter load 1, y of index 3 is voltmeter source 1. So this is a 0 indexed array. That's why whatever you want to plot, subtract 1 and put that in the index file. So now that we have this, I'm going to go at this point of time. Let me just leave it as it is. I'm going to go and first copy this file, close without saving. I don't have to save it, I'll go later. Let me copy these two. Let me copy rather this file to this directory. This is the directory where my current simulation is. Let me copy it here. So I have copied this file into the same folder as my circuit simulation. Okay, and it's very important. Try to maintain all your circuit simulations in different files. So now that this is done, let's now start generating plots. We don't need the simulation to end. The simulation can continue. That's not a problem. So let me open it here. Okay, so let's say I want to plot this file. Let's say I want to plot voltmeter source 1. As I said, we need in that case whatever is the index file. Okay, simulation is over. That's very convenient. Whatever is done, take away 1. So we want this number 4 to be plotted. So it has to be number 3 in the array. So let's put this as number 3. Save it. Let's come below to the command line and plot the file. So I'm going to say the same command, Python plot file, because it's a Python file. So if it's a Python file, it has to be placed, it has to be run with the Python command. So you see, and this is my plot. So you see what this is. Let's go. You can zoom in, and the best part is this is MatPlotLib, so you can do all the zoom in functions. So you can zoom in. This is your file. So this is how this voltage looks. This is when the diode conducts. So let's go back and check out some more options. So the next thing you want to check out is, of course, how would you plot two variables together? So for that, let's comment these two lines out, right? This is something you need to remember. Do not have several commands together, because remember, if you plot several plots, it will only plot the last one. So don't bother. If you're not plotting one file, just comment it out. So let's come here. This is plotting two variables. If you want to plot two variables, all you have to do, or even for that matter multiple variables, all you have to do is plot it together in this form. So let's go back and check it out. Let me now instead plot the currents. Let me plot current, that is the source current and the load current. So let's come back here. As I said, always check the index. I am plotting number 2 and number 3. So which means I have to plot here the index 1 and 2. And that's exactly as it is. I don't have to change it. So let's come back here and let's run the command again. And you see this is the new plot. As before, let's zoom in. So you can zoom in. So this is the input file, and you see this is when the diode conducts. This is where the diode conducts. You can zoom in. This is how the diode conducts. This is when, and when the diode conducts, the voltage rises. So you can actually even zoom in further here. So you see the load current increases. The load current increases because the voltage is rising, because the diode is conducting and is charging the capacitor. So this is how you can actually debug your simulation. This is how you can actually learn power electronics with simulations. So now I'm going to show you the last feature, and that last feature is how you can actually scale different functions. Let's go back and comment these two, because let's get rid of this. So now what happens if I want to plot the voltage and the current? The voltage and the current are very different. So I'm going to go to the last two lines. You see, plotting 3 variables and 1 variable with a scale. So let me do the same thing again. Let me plot now, this time let me plot the current, the source current and the load current, but now let me also plot the source voltage, but let me scale it down by a factor of 5. Okay, so you see here, there is, for that reason, there is something called scale waveform. If you say scale waveform, you need to pass 2 parameters. You need to specify which variable you want to plot, and the last, you need to give the scaling factor. Here I've given a scaling factor 2. So let's go back and find out where is my source voltage. So my source voltage is at number 4. So as before, take away 1. So it should be number 3. And it is number 3. Only thing, I want to scale it down by a factor of 5. So which means I have to scale it down by 0.2. Let me save this and let me plot the file again. And this is everything together. So let me again, you can zoom in. So you see, by doing this, by scaling this voltage, now they are at the same level. And because they are at the same level, it's now much easier to debug. Let me now zoom into this. You see, this is when it starts to conduct. And that's when it starts, the voltage starts to have a glitch. Because this conducted voltage, this current now produces a drop across the inductor. And because it produces a drop across the inductor, it now produces a glitch in the voltage. Because look at how large this current is. If such a large current passes through the inductor, that's going to produce a drop in the voltage, which is going to again produce a drop in the voltage input to the diode rectifier. So this is how you would simulate. This is how you would actually check out the simulation. Let's do one more little example. Let's plot even the output voltage. That's number 5. Alright. Now also, let's now, instead of plotting, now let's do that. What that means is I'm going to copy this last. Always plot every plot with respect to time. Okay, so you're plotting a file, also plotting a variable, also make sure you add the time points variable. So that's a scale waveform. And now as before, let's go back here. Voltmeter V out is at number 5. And if it is at number 5, we should take away 1, which is number 4. So let's put this at Y4. Now let's change the scaling a little. Instead of 0.2, let's make this 0.3. That is, I'm only decreasing this by a factor of, let's say around 30%, by 33%. So that's all for now. Let's come back here and let's plot this file. So you see, now another one has appeared. And this is my load voltage. So let's go back here and let's check it out. So you see, let's go zoom. So you see what's happening. This is when the diode starts conducting. When the diode starts conducting, the output voltage begins to rise. Why? Because this current is now charging the capacitor. And because it's charging the capacitor, the voltage begins to increase. Even though the input voltage is dropping, the input voltage drop is a glitch. It is not so large that the output capacitor actually collapses. Whereas if we go and zoom out, when the diode stops conducting, let's say this period, you see this is when the diode stops conducting. After this, the voltage starts to fall. Because once the diode stops conducting, the capacitor starts discharging across the load. So this is when the capacitor voltage begins to fall. So in this way, you can actually use MatPlotLib and this plot file to actually debug your simulations and also to learn how circuits work. So at this point, that's all from me. And I think this is pretty much. The plot file is also in this file. And as I said before, only thing, make sure everything is in one directory. Your circuit files have to be in one directory. Your simulation files have to be in one directory. And of course, lastly, the plot file also has to be in one directory. So make sure this is done. Otherwise, that's all. There's nothing more to do. Feel free to play around with this plot file. This is just a sample. There are lots and lots of very advanced plotting commands in MatPlotLib, and you are very, very welcome to use those. For example, you can use subplots. You can have array plots. You can have 3D plots. There are wonderful, wonderful functions in MatPlotLib. I don't go into it that much, but you're very welcome to. So that's all for now for this lecture. Thank you so much for watching. If you have any doubts, feel free to email me. Otherwise, I'll see you in the next lecture. Thank you again. Bye-bye for now.